Now we're going to carry on with the proof of the snake lemma. So recall the context of that. We had these chain complexes u, v, and w, differentials d going down like this, and then we had a short exact sequence of chain maps. So we've got these i's from u to v, and these p's from v to w, and the i's are injective, the p's are surjective, and the image of I is equal to the kernel of p. Because I is a chain map, di is id, that means this square commutes, and p is a chain map, so pd is dp, so this square commutes. And if you recall in the statement of the snake lemma, there was this so-called connective homomorphism delta. So we need to work towards the definition of that map delta. And that's going to rely on this group that we're going to define just now. It's called the group of snakes. Okay, so a snake for the above system is a system CWVUA with the following properties. Firstly, C over here is an element of the homology group HNW. And then W is going to be a cycle in Zn of big W that represents C. Okay, so C is going to be bracket W. Right? So remember, ZNW, that's the cycles in Wn. So that's a subgroup of Wn. So W is here, it's in ZNW, which is contained in Wn. And then HNW is a quotient, ZNW mod BNW. So we've got a surjective quotient map from ZNW over to HNW. Yeah. And so W represents C, so C can be written as square bracket W. Then next V, so you've got WVUA here. Okay, so this middle element V, that's going to be an element in the group Vn, and it's going to have the property that PV is going to be equal to W. So under this map P here, the V gets mapped to W. The next element U is a cycle in Zn-1U with the property that IU is equal to dV. Right? So here, remember, you've got your UN-1 here and Zn-1U, that's the subgroup of cycles there. So U is supposed to be an element of this subgroup of cycles with the property that if we do IU, so we push across using this map I here, then what we get is the same as dV. So it's the image of this V under this vertical map T here. And then final condition, this last element here, A, so that's supposed to be an element in Hn-1U. That's got to be represented by U. So A is going to be equal to square bracket U as an element of the homology group Hn-1U. And we'll also say that, so this list here, CWVUA, we're going to say that it's a snake from C to A. So that's what we mean by snakes. So and it's pretty easy to see that the snakes form a group under addition. Right? We add together all of these conditions here are compatible with addition. So if we have two snakes, we can add them together and they'll get a new snake. So the first basic fact is that if we've got some C here, then the claim is that there exists a snake that starts with that C. So to prove that, well, firstly, of course, C is in HNW. HNW is by definition just this quotient ZNW mod BNW. So the C, we can choose some representing element for the corresponding coset, call it little w. So W is going to be an element here, and C equals square bracket W. So that's kind of our first step in building a snake. And for the next step, with this IVW short exact, so in particular that means that this P here is surjective. So because P is surjective, we can always choose a V here that gets mapped to that W there. So we can choose a V here, PV equals to W. Okay. So now we're going to use the fact that that P is a chain map, dP is PD, so this square commutes. And so if we go this way and this way, that's the same as going this way and this way. Okay. But what happens if we go this way and then this way? Right. So we go from V and we go across here. We get our W. That's how we chose V. And then, but W, remember, was a cycle. It's in this group ZNW, which is just the kernel of D. So when we do dw, that just gives us 0. Okay, so if we go this way, we get 0. That means that if we go this way, we get 0. Okay, so we're saying that P of dv is the same as D of PV, which dw is 0. Okay, so we've seen that PdV is 0. In other words, dv is in the kernel of P. But the sequence here was short exact. That was our basic assumption that we started with. So the kernel of P is equal to the image of I. So that means that we can choose some u here, with I of u being equal to dv. But to make a snake, u is not just supposed to be an element un minus 1, but it's actually supposed to be a cycle. It's supposed to be in Zn minus 1 u. So we want to ask ourselves whether du is really equal to 0. Well, if we look at I of du, then because I is a chain match, same as d of iu, but iu is equal to dv. That was how we chose our u here. So we've got so here this diu is ddv, but d squared is 0. So so that's equal to 0. So I of du we're seeing is 0. But again, this thing's supposed to be a short exact sequence, so I is injective. So if I of du is 0, then that means that du is already 0. So that proves that u really is a cycle. It's an element of Zn minus 1 u. So we can write this u over here instead of over here. Okay, and now to make a snake, where a is supposed to be equal to square bracket u, but we haven't seen a already. We've got free to choose what a should be, so we just define a to be square bracket u, and then that gives us the snake that we wanted. Okay. So we've proved that for any c here, we can fill in the w, v, u, a to make a snake. But we also want not just an existence statement for snakes, but some kind of uniqueness statement. And the relevant uniqueness statement is this lemma here. We've got two snakes that have the same starting point, the same c at the beginning, then they also have the same end point. So suppose we've got two snakes like that, they both start with c, then we can subtract them, and we still get a snake. Okay. That's as we mentioned when we introduced the definition of snakes, or all the conditions in the definition are compatible with addition and subtraction. So you subtract two snakes, we'll still have a snake. So now we've got a snake, and the two snakes we started with, they both started with c, so when we subtract them, we get a 0 at the beginning. And we want to prove that the two snakes we started with have the same endpoint. In other words, that this snake, the difference, has to end with a 0. So we want to prove that this a here is 0. So let's consider what it means for this to be a snake. So the first condition was that and this is some element in the homology group, and the first condition is just that this 0 is equal to square bracket w. Okay. But remember, what does this square bracket w mean? That's the coset modulo boundaries, modulo the image of d. So if we say that coset is 0, that means that w is in the group of boundaries. That means it can be written as dw prime for some w prime up in wn plus 1. Okay, so now so we've got this w prime in w, and remember that our p is a surjective map from v to w, so we can choose some v prime here in vn plus 1, with this w prime being equal to pv prime. Okay, so putting this together, if we take w, okay, so w, remember, was dw prime here, and then the w prime is pv prime, so we can write this as dpv prime. But then, because p is a chain map, we can also write that as p of dv prime. Okay, so this is the first of a couple of things we need to, a couple of equations we need. We're going to call this one a, that w is p dv prime. Okay, so then remember here we've got this snake here, and the second condition for a snake is that p of v should be w. Okay. So we're going to call that b. Okay, so we combine these two things. So PV is the same as P of dV prime. They're both equal to W. So that means that if we take P of V minus dV prime, that's just 0. Okay, so by combining A and B, you see that P of V minus dV prime is 0. Or in other words, if we take this V minus dV prime, that's in the kernel of P. But we were assuming we had an exact sequence, so the kernel of P is equal to the image of I. So V minus dV prime is in the image of I. So that means we can find some element U prime. This is going to be in UN, with V minus dV prime being equal to I of U prime. Yes, this element is in the kernel of P, so it's in the image of I. It could be expressed as I of something. Okay, so let's apply d to both sides of this. So you get dv minus d squared v prime. D squared, of course, is 0, so on the left-hand side we've just got dv. On the right-hand side we've got diu prime, but di is the same as iu, so we've got idu prime. So we've got here dv is idu prime. But let's go back to here, right? The this sequence is supposed to be a snake, and the next third snake condition says that dv is iu. Okay. So here we've got dv as idu prime, and we also have dv as iu. By subtracting those facts, we see that I of u minus du prime is iu minus idu prime. That's dv minus dv, so that's 0. So I of u minus du prime is 0. But remember, I was injective. I comma p is a short exact sequence. So I of u minus du prime is 0. That forces u minus du prime to already be 0. Or in other words, u is du prime. So in particular, u is d of something. It lies in this group here of boundaries. U is in b at n minus 1u. Now the last snake condition said that a is square bracket u. Okay? And remember, square bracket u, that's just notation for the coset u plus bnu prime. But here we've seen that u is just an element of bnu prime. So this coset is just the 0 coset. And that means that a is equal to square bracket u, which is just equal to 0. Okay, and that's what we were supposed to prove, that this subtracted snake here that started with 0, it does indeed end with 0. So we've proved that we've got two snakes that have the same starting point, and they also have the same end point. So this allows us to make this definition here. If we've got any c and hnw, we are going to define delta c and hn minus 1u to be the end point of any snake that starts with c. So lemma before last said that that there exists a snake that starts with c, and the previous lemma also said that if you take any two snakes that start with c, then they have the same endpoint. So that means that delta c is actually well defined. And as we mentioned a couple of times already, sum of two snakes is a snake, and using that you can see that delta is actually a homomorphism. So that defines the map delta, and that will do for this video. In the next video we'll start proving the properties of this delta.